Morning is Dr. Gerald Gwinner from the Department of Physics and Astronomy in the Faculty of Science, and I have to confess right now, when I was doing my training, I took one physics course because I had to. It was a requirement to get to go on and do medicine and do some other things. So I took a physics course, and it was a very utilitarian course. I took it to do what I had to do with it and probably forgot every single thing that there was about physics, with all due respect. I didn't, it was not fun. But Gerald comes to us from a very fine training background at the premier physics institutes in Germany, universities of Heidelberg and Würzburg. He comes also from State University of New York at Stony Brook, which is a big institution, and University of California, Berkeley, where I also did some of the training. So we were comparing notes about Berkeley, and he was complaining that it was a little too warm for him. Well, he came to the right place to escape warmth. He's going to talk to us a little bit about some of his work with, and I did this all by myself, I can pronounce this, laser-trapped francium at the isotope separator and accelerator radioactive beamline at the Tri-University Meson facility in Vancouver. How about that? I have no idea what that means, but he's going to tell us a little bit about that today. So please welcome Dr. Gwinner.
Thank you very much. In fact, actually, I'm talking about a slightly different experiment, but in principle, they aim at the same thing, namely trying to figure out where the universe is coming from and where it's going. So this is very basic research, probably as basic as it can get. We're not aiming, let's say, for applications, and so in general, this is quite probably a change from the previous talks, which I really enjoyed a lot. I predicted all these Big Mac predictions based on what the label is, and they're still good, I have to say. Anyway, so yeah, so my title is The Theory of Everything, Making Our Way to the Planck Scale. What that means, I hope, will become more or less clear during my talk. So yeah, I've been here for a couple of years at the University of Manitoba, and now we're warping a little bit back through this space-time fabric onto my first slide. Took a little longer. So the two most extreme frontiers in science that you can imagine is, on one end, cosmology, which looks at the whole universe. That's the largest scales we can imagine. And the very smallest one is subatomic physics, particle physics, where we look at ever smaller things. And so, like with the arrogance of a physicist, you could say everything else in between is details. But yeah, if you get an overdose of sodium and you get heart disease, then you probably would not think that that's a detail. It's actually then more important than the Planck scale. So this picture here shows actually that's an image of the sky taken by this Planck satellite looking at the microwave radiation coming from all parts in the sky, looking at us. And this, we'll see in a moment, actually contains a lot of powerful information where the universe is coming from. In this earlier talk about visualization, this Swedish guy with this cool data plot actually pointed out that this graph contained 120,000 data points. So here we could say this is made up from 10 to the 80 protons that make up the universe roughly. So these very two extremes, they're coming, particle physics and cosmology, they come in many ways. You know, the other extreme ends of physics, astronomy, and for the longest time, I guess that's not me shaking it, no, it must be somewhere the projector, yeah. The universe is moving, so they were quite distinct. I mean, you look at stars, no, that's one thing, and then you look at tiny little things in your lab, that's nuclear and particle physics. However, cosmology and particle physics are increasingly interwoven. The whole thing is really one. And I would like to motivate to you where that's coming from. I should give credit here, image credit. I collected some nice pictures here from this PASCOS conference, their conference poster, that basically shows that this universe, this map of the sky of the universe that we have seen previously, that is actually coming from particle physics at the beginning. Basically, this is tracks from subatomic particles in a collision at one of, let's say, these big accelerators that subatomic physicists operate, sort of blowing this apart. It could also be like an egg flying apart with some death rays coming out. Anyway, it looks pretty impressive, so I adopted that. So here, I want to make this connection. So this is the evolution of the universe. Now, if I want to make an evolution plot, a time evolution, basically, space-time is four-dimensional, 3 dimensions of space, of course, that we're used to, and then time. That's pretty hard to plot, especially on a 2-dimensional screen. So what we do here is we make a time scale here, and the universe here is basically a slice. It's a 2-dimensional universe. So here we are today, now, basically with galaxies, and with galaxy stars and planets, and in one of them there's us, and in one of them in a building there's me giving a talk, and so on. And so then we look back in time. The universe, we know it's been expanding, so this 2-dimensional universe is getting larger with time. We go back, the universe is a little smaller, galaxies were forming at some point, and if we go even further back, at the very beginning, we think, I mean, that's only a theory, but there's a lot of facts speaking for it. There was the Big Bang, where the whole universe suddenly came sort of out of nothing, so to speak. Whatever nothing means, I'm not really clear. But the point is, the universe was very tiny, much, much, much smaller than the smallest things that we can see. It came basically out of nothing. And so in the early universe, there were basically all these very small particles coming out of nothing, radiation particles created, annihilated, and then this whole thing expanded, first very rapidly through an age called inflation, and then afterwards slower, and that's then where stars formed, galaxies, and so on. So this is how we're looking back, and I guess it's like defying the people who organized this. They said, look 25 years into the future. I say, no, I'm not doing this. I'm going to look 50 billions into the past, 50 billion years. But the methods that are being developed to look at these very distant times, the beginning of the universe, that's of course stuff that has happened over the last half century and are now really so like in a golden age where there are many more inventions and discoveries made. So this is an exciting time for people working on this. So in this early age of the universe, what can we do here? When we work with very big telescopes, basically with big telescopes, you look farther and farther away in the universe. Fainter and fainter galaxies you look at. That means they're farther away, since light has a finite speed for the light to reach us from there. We actually look into the past. The Andromeda Nebula, like one of the closest galaxies, is about 2 million light years away. So the light that we see now in a telescope that reaches us left here 2 million years ago. So effectively, we look at Andromeda as it was 2 million years ago, which on this scale is nothing. But if we look further and further out with really big telescopes, we can see galaxies that are farther and farther away. In fact, we can look all the way up to here, basically. For example, these quasars, those are galaxy-like systems that are so far away that they almost look only like a star image to us. They're so small because they're so far away. So we can look that far, but we cannot look much further with these astronomical methods. However, with particle physics, subatomic physics, that's done in the lab, you can start studying what's happening here when basically the universe was these tiny particles being created and interacting and then expanding. So this is the other frontier, so to speak. So we study the very small over here and the very large with the astronomical methods, and they both sort of get combined these days into an overall picture. So that's sort of the idea about that I want to convey in this plot. So now I said to understand the large or understand the whole, we actually need to understand not just the large, like astronomy, looking into the cosmos, but also the small. But small, what does that actually mean? Like a millimeter, is that small? Like a thousandth of a millimeter? The atom is like the largest, what they call a microscopic particle that was discovered, established kind of 1910-ish, that this exists, a nucleus with electrons going around. That's about 10 to the minus 10 meters in diameter. That's really small. That's less than a billionth of a meter. Then shortly afterwards by Rutherford, actually, he was, while he was mostly afterwards in Britain, he actually worked for a long time in Canada at McGill, and there's now a centennial there in his honor. Actually, not a centennial, I think it's actually in England, but a lot of the work he did in Montreal, he established the existence of a nucleus, which is 10 to the minus 12 centimeter. That's like only 100,000th of the size of an atom, or 10,000th of the size of an atom. And then later we found that the nucleus is made up out of nucleons, protons and neutrons, and they're another factor of 10 smaller. And then they are made up out of quarks that are on the inside that are even smaller. And so that's what we observe right now. And so where are we heading in the future? This is an old figure, so 1980s, not now, but we're still working on this. And so where this is going, how do we probe smaller and smaller distances? Very early on the creation of the universe, things were even smaller. So we want to know, where's this coming from? I mean, why is there quarks? What's making quarks? Is there an end to it? And so for that, we have to look at smaller and smaller distances. What does this mean? For telescopes, if you want to look further and further away, it's pretty straightforward to see. You want to build bigger and bigger telescopes because they have to gather more light to see fainter objects. In subatomic physics, it's sort of the other way around. And I think I can demonstrate that by this famous Heisenberg uncertainty principle, which is probably the second most famous formula in the world after Einstein's E equals mc squared. That's the principle of quantum mechanics, that if you want to measure something of a size delta x, at the same time, you can determine the momentum, or like the motion, so to speak, of a particle, of an object, only to an accuracy delta p, such that this is roughly fulfilled, where h is a constant, Planck's constant, which is an incredibly small number. But if you go into the microscopic world, it turns out if you want to look at very small length scales, probe something very finely, like with a microscope, but even finer, then you need very large momenta, or momentum, and that's, so to speak, mass times velocity. If you're at high school physics, then large momentum also corresponds relatively to large energy. So to look at smaller and smaller scales, we will need larger and larger energy. That's why people build these gigantic accelerators like the Large Hadron Collider at CERN, which costs probably in the order of nearly $10 billion. Because you make incredibly powerful collisions between particles to study their interactions, or actually find new particles that we haven't found yet, elementary particles that for example, would explain what quarks are, or actually open a completely new frontier in this business. So what's there ultimately at very small length scales? One of the hypotheses that I'm sure that you heard about is string theory, that says at these incredibly small length scales, I mean, this is insanely small, then this is just outrageously insanely small. Strings, there these particles basically these loops, and all the things that we observe are basically what people speculate, that's all theoretical at this point. Basically vibrations of these loops are excitations that make the more complex objects that we see at larger length scale in the world. But this is a hypothesis, but people would like to go there. The only problem is we have to just go 20 orders of magnitude smaller to go there. How is that possible? Before I get to that, I would like to just quickly introduce these interactions that we deal with. Those are called the fundamental forces of nature. This would be the way such particles interact. Two of them we're very familiar with. One interaction of force is gravity. If you fall from a ladder, you can convince yourself that gravity is a powerful force. The other one that's very, very important is the electromagnetic force. It's responsible for basically chemistry happening, molecules and solids forming out of atoms. So the whole world around us is really, it's all electromagnetism. Gravity sort of holds it on Earth, but the reason why this is wood, is it actually, or is it fake? I don't know. And then there's this plastic. That's all because there's chemistry going on that's dominated by the electromagnetic force. So those we are familiar with. But then there's also the strong force. That's a force that holds the quarks and the nucleus together, makes the nucleus. As the name says, it's a very strong force. And then there's a weak force, which you could guess is a weak force. That's responsible for something, for example, called beta decay, radioactive decay you might have heard of. To our knowledge right now, those are the 4 forces that exist in nature. And those we study in subatomic physics. And one important thing is these interactions, they all have very different strengths. The strong, the weak interaction already indicate that that's the case. But let me show you, introduce this plot. This axis here is an energy axis, low energy, high energy. It's an electron volt. Electron volt is a convenient energy unit in physics. If you take an electron and accelerate it through a potential of 1 volt, like roughly a 1.5 volt battery, the voltage between the 2 terminals of that battery, you give that electron an energy of 1 electron volt. So typical energies in the world around us is about like a 40th of an electron volt to about a few electron volts. That's where chemistry, electromagnetism here happens. And so that's somewhere over here. We don't even bother including what's actually in the real world in our plots, because we think about much higher energies. But the point is, we can look at these interactions as a function of the energy by, for example, making collisions in accelerators in colliders between particles, between protons and electrons and so on, at various energies and study these forces. And so at low energy, it turns out the strong force that holds the nucleus together is by far the strongest force. That's why it's up here. This is like a scale of the strength of the force. The electromagnetic one is the next strongest. The weak one is a lot weaker. And gravity is incredibly weak. Gravity is actually by far the weakest force. It's like, well, but it seems to us the most important one. But that's only because we are neutral. All our bodies are made out of positive and negative charges in equal amounts, so there's actually no electromagnetic force. If we were all made just out of protons and there were no electrons, my body would explode violently, overcoming any gravitational attraction. And sometimes my physics lecture, probably students would wish that would happen. In any case, gravity is very weak. But then as people study how these strengths change as you make the collision energy in these experiments higher, they found that at a certain energy that can be reached now at about the most powerful accelerators or colliders in the world, the weak and the electromagnetic force suddenly, they come together in strength and they suddenly form one phenomenon that's called the electroweak force. So at high energy, there's not electromagnetic and weak, there's only a unified force between them. This has been observed. This is where we are right now with our technology for subatomic physics. But people can study and theoretically predict how these strengths is changing. We can extrapolate this. And the prediction is that at a much, much higher energy that we cannot reach right now, the nuclear force and the electroweak force combine to one common phenomenon that has one strength. That's called grand unification. And that at an even higher energy, their gravity joins them. It becomes gradually stronger, and the other ones come gradually weaker. And here they unify, and that's called the theory of everything. I mean, this has not been observed. We can't go there experimentally, but this is where they would unify, and this then all forces that we know are explained by one phenomenon, so to speak. And this could be explained by string theory, or sometimes you might have heard of quantum gravity is another contender that tries to predict what's happening here. So that's what we want to probe, and this might, for example, be very well like the highest sort of energies with which we deal for elementary particles. There's some ideas that it might be over with, so that there's nothing sort of beyond that. I'll come back to that. So in any case, having experiments here, how can we make predictions of what's happening over here? That's sort of our goal to make progress in this direction. And so this is basically the same plot. It's not very good, I apologize. I wanted to redraw it, but I got too tired last night. So I just, like we all do it now, I ripped it from the web and kept it that way. This is now basically tilted over at very low energies. That's where we are here. 10 to the minus 4 electron volts, a little bit more than that. That's where, like now, our world is sort of taking place, except for a bunch of crazy physicists who do stuff up here. But all other people are down here. And so there we have these 4 very different forces, and then at these highest energies that we can make, we get this electroweak unification. So that's all down here. that corresponds, these high energies, they correspond to times after the Big Bang. So at the beginning of the Big Bang, everything was very concentrated, everything was very energetic before it flew apart. So very high energies is very early after the Big Bang. So up here, this where this theory of everything business, this quantum gravity or string era is happening, that's about 10 to the minus 44 seconds roughly after the Big Bang. It's kind of like a short time. And so all these energies at which we can probe particle interactions correspond to roughly a time when this was sort of relevant in the universe, if you want. And so, again, this is the world around us, except for a few elite particle physicists. And I'm actually a nuclear physicist, so I can say that without implying that I'm self-great. I just make fun of particle physicists. Because they despise us as nuclear physicists. But anyway, so that's where we can be, and that's where we want to talk about. I mean, that's general. People always want to talk about things that they actually have no idea about. That's natural. So we want to infer what's happening up there. So what can we do? So this is this area up here where this unification happens, 10 to the minus 44 seconds. 10 to the 19 giga-electron volts. That's accelerating particles in an accelerator with 10 to the 19 times 10 to the 9 electron volts. Even in a thunder, lightning, you don't get that kind of voltage, so we can't get there. That corresponds to a length scale. If we probe, according to Heisenberg uncertainty principle, if we probe nature with particles of that energy, we could probe length scales of 10 to the minus 35 meters. That's that Planck scale that I mentioned in the title. So that's where we want to go. So we have to simply extrapolate here by 10 to the 2, by 10 to the 17, by 17 orders of magnitude. We have to extrapolate. So that's kind of ambitious. So how can we go probe the Planck scale without really going there? The point is Planck scale physics has ramifications at lower energies. You're probably, not just in physics, but everything around us, there's nothing ever that's valid in one place, and then it's abruptly no longer valid. Mathematicians can make something like a theta function, which is 1 here, and then suddenly 0. Everything in physics and other sciences you find out in real nature, everything like goes smooth generally. So if something is happening somewhere, you see some ramifications of it somewhere else. But it might be very weak. But if we make very, very, very precise measurements at very low energies, we can actually hope to find a glimpse of what's happening at the Planck scale. And the approach of our experiment would be the following. These fundamental forces that I just described, or interactions, are intimately connected to like symmetries that they follow. And those symmetries or their violation can be probed. And one symmetry that we look at is called Lorentz symmetry. Basically, Lorentz symmetry simply means, I keep this short, the theory of special relativity. All these forces, the way they're described by theories that describe the world, so far the particle physics world, as we know it right now, are firmly based on special relativity. That's an underlying assumption. So they have to fulfill the symmetries that special relativity forces upon them. And then we can look whether that's actually true. And so I want to do this by like quickly make an intro to special relativity. So now we're coming down to Earth, going to trains, because actually I think that the things that I'm talking about, all you basically need is to understand that the relativity that we do by looking at Pythagoras, which all of you, of course, can do, including myself. Even sometimes I get it wrong. So to make a simple example here, special relativity, for example, as it relates to velocities. The velocities that we experience in daily life are much, much, much less than the speed of light. Speed of light is 300,000 kilometers per second. So it's basically going to the moon in 1 second. That's a very fast speed. Everything else we do is much slower. So and relativity only becomes important when you reach speeds that are close to the speed of light. That's very difficult for us. And so normally we don't notice special relativity effects, and that's why it took so long for them to be discovered. So one example is the addition of velocities. So suppose we have a train here that goes 200 kilometers per hour. So that's not necessarily North America, but elsewhere in the world, that's quite common. And now I have a guy in there, he's sitting there, and I don't know, he's either hungry and goes to a restaurant, or he has to go pee, so he has to go to the restroom. So he walks in the train. So he walks with 5 kilometers per hour in the train, Now if I stand here at the tracks and see this coming by, the train moving and the guy moving with the train, inside the train, then we would say, of course, we see the guy coming by with 205 kilometers per hour. That's natural. This is kind of true if you made this measurement. This would come out, but if you made this measurement very accurately, it would turn out that these, due to relativity, these speeds actually do not add perfectly. It's actually a tiny little bit less than 205 kilometers per hour. And to do this in a more extreme case, to illustrate this, we make something that actually Einstein invented, and that's why the name for it is German, Gedanken experiment, means thought experiment. It's something you can't really do unless you believe in Star Trek, but you can think about what would happen. So let's say the Enterprise is traveling at half the speed of light, 150,000 kilometers per second, toward the Klingon ships and fires a photon torpedo. So that the Klingons, are they seeing the torpedo coming at the added velocities, this plus the speed of a photon torpedo is light, so it travels with the speed of light. Do they see it at 450,000 kilometers per second? Actually, the answer is no. They see it with 300,000 kilometers per second. No matter how fast I move with my source of light, you always see it approaching this light with 300,000 kilometers per second. That's the weird thing about, and basically relativity, special relativity can be basically derived essentially from that it doesn't matter. Like if I throw a baseball with a certain, let's say 100 kilometers per hour, I probably couldn't do, but if I did this, and now I ran and I threw it, then I would actually, then I could throw it faster at you. I mean, we intuitively expect that. With light, it doesn't work. No matter what, as long as it's in vacuum or in air at least, we always see light coming at us with 300,000 kilometers per second, no matter how the source is moving. And from this principle, the speed of light is not dependent on the motion of the source or the observer, and its value in vacuum is always this number. We can basically derive special relativity. And so this is relativity on one slide. I just want to show you what the general upshots are. We have a body here. It has a length of L0 when it sits in front of us, and we measure its length with a ruler. There's a clock in there that ticks every second. Say, if I'm sitting in front of it, it's not moving relative to me, and it's ticking every second. But then we pack this into a really fast car, let's say a Ferrari, and then we move really fast by the street. And now there's someone standing by the curb again and trying to measure, let's say with a camera, how long this thing is as it's moving by and how fast that clock is ticking. So for that, you need a movie camera. And what the guy in the street, which we call the laboratory here, finds is that if this thing of this length L0 is moving, you measure it to be a little bit shorter. It only has a certain length L, and the clock ticks more slowly. And so that there's an exact prediction by relativity. This thing is shorter by a distance, by a factor 1 over gamma, where gamma is defined this way. It's called the gamma Lorentz factor, where this is the speed that we move with relative to the speed of light. So any object that's moving is contracted. That's called Lorentz contraction. And clocks that move relative to you are dilated in time. They tick more slowly. That's called time dilation. Those are predictions of special relativity, and they have been confirmed. And a really fascinating manifestation of special relativity is this time dilation, one of these effects. And I find it fascinating because that's what I measure, so naturally I would say it's fascinating. The moving clocks tick more slowly. That means there's no absolute time. So these famous clock comparisons in action or crime movies, they don't work, because if the guy then gets afterwards in a car and drives off, his time is out of sync again. But probably not enough to be a problem for their purposes. So now I want to basically build a clock and show how we can calculate how this gamma factor comes about. How do you make a clock? I mean, normally it's a cuckoo clock or something. You have a pendulum, and the time it takes for the pendulum to go back and forth, that defines your second. I want to make something where it's not a pendulum, but it's a light beam that's going back and forth. So we make a clock by having here a light source, a flash lamp. It sends at t equals 0, it sends out a light wave that travels in all directions. Part of it will travel up here. A mirror will send it back, And when it arrives back down here, a detector will detect it, and that's 1 time unit. If this distance stays constant and the speed of light is a constant, then this turnaround, this travel time, this round trip time is a constant. And so you could build a clock by whenever the light comes back and triggers the detector can trigger a new flash, then there's a new one coming, so you get something that ticks regularly. And so we can build something like that. So I put this in a car, which you will see why in a moment. So this is 3 meters, say. So at t equals 0, we trigger the flash lamp. So after 2.5 nanoseconds, this light will have expanded in all directions like this. It's like a shell of light. And after 10 nanoseconds, oh, a little bit too far, about 10 nanoseconds, it reaches the mirror, and the part that hit the mirror will be reflected back. So that will be a wave that's coming back. And after 20 nanoseconds, it reaches the detector, and this is still, I did this in German, this slide, so click has a K. And so this is so the round trip time here of 20 nanoseconds defines this time. So now we do this so that the time it takes is, something is the distance traveled by the velocity. T is S over V, if you want. So the time is 2 times this length L, because it's a round trip, that's why I have this 2, divided by the speed of light. So now we do this with a really fast-moving car. So it's a Ferrari, so it can go 225,000 kilometers per second. So that's 3/4 of the speed of light. And now I'm standing by the curb. And at t equals 0, this thing starts, there's the flash. But then remember, we said wherever we stand, we see light going away wherever it goes in 300,000 kilometers per second. So this light cone is not traveling along with the car, but it's expanding with 300,000 kilometers per second around the original position where the car was when the flash happened. And so now that this is expanding with the same speed, but after 10 nanoseconds where it would reach the mirror is gone. It's over here, so it missed the mirror. So you have to go a little bit longer. You have to go 50 nanoseconds to reach it over here. And then it comes down, but in order to reach this detector, which is now over here, it actually takes 30 seconds. So if you travel at 3/4 of the speed of light, this clock clearly ticks 1.5 times more slowly. Did I say that right? I mean, it ticks more slowly by a certain factor, like 30 over 20. And so basically, this is the light, the distance that the light has to travel for the moving, when you observe the moving clock. This is the distance that the light has to travel for the clock at rest. They're clearly different. And this is the distance that the car travels before the light comes back down again. So if it's a triangle, this one is the speed of light times the time it takes for a click over 2, because we only measure this and not the whole, because I want to make a right angle triangle here. This is the speed of the car times the time it takes for the click to happen for the moving car over 2. That's this distance. And this height here, that was from the earlier experiment, the time it takes for a click over 2 for the stationary clock times the speed of light. And so we have Pythagoras in this triangle. We basically just have this. I just copied this over. It's on this slide here now. So we only have to solve that for t prime as a function of t to find what the ticking in the moving clock is relative to the ticking in the regular clock. And you can do this. It takes a while, but this is trivial to do in many ways. This is exactly this gamma factor. And so for an observer moving with respect to a clock, it ticks more slowly by this time dilation factor. Since our speeds are always positive and less than the speed of light, this number will always be larger or equals to 1. If you don't move, gamma is 1. If you start moving, your clock is moving, then gamma will get larger than 1, can go all the way to infinity. So how big is that effect? The effect is kind of small for normal. What's the fastest speed that we can give a regular clock? Let's say a clock like this. I can pack it into a spacecraft that's faster than a bullet. Spacecraft, you can do maybe several kilometers per second. The time dilation we would see would only show up in the 10th digit. So you wouldn't notice this. We can easily measure this now with atomic clocks, but that would never be noticeable. If we go to half the speed of light, we get a 15% effect. That's noticeable, but not drastic. The biggest one, for example, electrons stored in this accelerator lab at CERN, those are electrons at 90 gigaelectron volt. They're so fast that actually for them, time, when we observe them, they seem to age 100,000 times, 180,000 times more slowly than normal. whatever normal electron is, I don't know. But I mean an electron at rest, so to speak. So there you have extreme time dilation effects, and you can get very bizarre results due to that. So what we really have to do to measure Lorentz symmetry very carefully is to make clocks that we can make very, very fast. And so regular clocks like this won't do because we can't get them faster than a couple of kilometers per second. And even that requires some spacecraft somewhere between here and the sun, say, which is not simple and to do. So we use basically atomic and subatomic particles as clocks because we can easily in accelerators make them very fast. And the idea here is that in an atom, you probably have heard of that, I mean, that in quantum mechanics, or it was found, and this was the beginning of quantum mechanics, that the electron orbits in an atom are quantized. An electron can only live on certain specific discrete quantized orbits. That's where quantum physics is coming from, the quantized orbits. And when an electron jumps from one to the other one, it has to like give off some energy or absorb some energy. And this energy here, according Einstein found that he actually got the Nobel Prize for that and not for relativity at the time, that this energy that the electron has to send out when it goes from a higher orbit to a lower, that one is a constant times the frequency of the light that's being sent out when the electron jumps down. So the frequency of light that comes out of such an atom, that frequency, that's a very precise clock. And if that atom is moving relative to us, that frequency is changing. And so what we do, this is in Heidelberg, this experiment in Germany, there's what's called a storage ring. We inject accelerated lithium plus ions into this ring. They basically come in here, and then with magnets, they get bent around. And so at about 7% of the speed of light, they keep circling for many, many seconds in that ring. And then with lasers, we probe that transition frequency, putting electrons in this ion from one orbit to another one, and measure how that frequency is different from when we do the same experiment when the lithium ion is at rest and not moving. And so I don't think that I want to go into many details here. So this is this ring. The ions go around here, and we have to send in lasers from two directions to get the experiment more accurate. This involves all sorts of lasers in the green and the yellow. And we have to measure the frequencies of these transition in these atoms to a precision of about 10 to the 10. This is incredibly, that's not so simple to do, let's put it that way. And I think this is the most accurate measurement of any kind done ever at an accelerated beam. So this was a lot of difficulties. We had to work hard on that. One nice thing is to actually measure these frequencies. We used the frequency comb. We collaborated with the group of Ted Hensch in Munich. He got the Nobel Prize a few years ago for inventing this frequency comb, which was measuring these frequencies of light very, very simple compared to what was before. So we did this and we published. We confirmed special relativity at the 10 ppb level, which is like the most accurate confirmation of time dilation by quite a margin compared to what had been done before. But we did find agreement with relativity. So no hint yet of physics at the Planck scale. But the idea is that one pushes further and further. I mean, I don't think we really expected anything at this level. But of course, it takes decades of improvements and improvements in these experiments, and then every now and then there's suddenly a breakthrough happening somewhere. So you keep working on this, and we published this in a nice journal. These are some of the guys. They're obviously very happy. They're smiling when they work with these lasers that we set up in the basement there at that storage ring. It looks pretty cool. We have it dark. Hey, why is this? Not following my orders anymore. Okay, so you have these laser beams. It looks pretty neat. And when this came out, this publication, I was interviewed by the Winnipeg Free Press, and I think this is from I think this one too. The Sun came by too. There was on the day when the Bombers the last time made it to the Grey Cup. They beat Montreal. It's from nightmare to dream in just 4 seconds. For us, it was about 7 years that we had worked on this experiment. And we listed here right above World Diabetes Day, which makes sort of the connection to the previous talk. And we improved by a factor of 100,000 the original measurement. And in the interview, I said 10,000. And I just got it wrong. And they quoted me on that, which told me how careful you have to be when you talk to the press or when you actually filmed or something. It can be used against you. Let's thank the gentleman back there to working so diligently to record all this. maybe to my disadvantage, who knows. In any case, so on the way back from the Bomber game, the guy called me, the photographer, and said, can I swing by your house and take a photo of you? I said, yeah. It's like, well, can you go to your study? I was like, well, I don't really have a study. It's kind of like a mess, you know, with kids' toys and God knows what. I was like, well, do you have an Einstein book or picture? I was like, yeah, I have that. Well, hold the Einstein picture. And then we went to my porch. And he took a photo. So they went around the world, even in Iran, they commented that it's a century late, but Einstein's still on time. And down here, I really like this remark here. This is like, after 2 hours, I looked at my watch, a reviewer of a Wagnerian opera is said to have written, I found that 17 minutes had gone by. So for Wagner operas, obviously relativity also applies. I would also, before coming to an end, actually mention this. I mean, the idea is to do basic research here to find, is relativity right? Can we find something beyond relativity, which would be pointing at Planck scale physics? But there is actually an application for relativity, believe it or not. The GPS system that lets you sort of locate very accurately on Earth where you are. It's a network of satellites with very precise atomic clocks that are located in the sky, and your receiver gets signals from a bunch of them, and depending where you are relative to them, because of the finite travel time of light or of this radio frequency radiation, the timing difference between arrival of signals from different satellites tells you where you are. And this assumes that relativity is correct, and if it weren't, I mean, if general and special relativity were not taken into account, actually this would be off by about 1 kilometer per day. So this is serious business. I always say, like, that would be bad for yachting because 1 kilometer in the Lake of the Woods can kill you. And if a smart bomb is off by some distance, it would kill you anyway, but kind of, that's probably a bad example. To end, I would say, so I have to still now make the connection why this test of Lorentz invariance or special relativity has any connection to this Planck scale physics. Can we understand why Lorentz invariance actually should break down at these energies? So the idea is this Planck length, so these energies, where this unification, the theory of everything is what's happening, where string theory is taking place, so to speak, that corresponds to very short distances, 10 to the minus 35 meters. And so there's theories or predictions that this would be a universal smallest length in the universe. So this Planck length, which can be calculated in a very simple way from a bunch of constants, which is about this length, it's a universal number. Now what, so it's like any observer in the universe would agree on that length. But now if we have relativity, if I say this is my Planck length here, it's like a little larger than it really is, but let's say we zoom down, or zoom in, this length is the Planck length. But then someone's driving by in a car and says, oh, but I see this Lorentz contracted, so in my frame your Planck length actually looks shorter to me. But it says, if this is really the shortest universal length, it cannot be. It must be in all frames, whether you drive in a car or fly by at some very high speed. It must always be the same. Clearly, relativity does not predict this. So relativity must break down somewhere down there. And the idea would be that, for example, space-time would be discrete at these lengths. Lorentz contraction is not valid because the Planck length should be the same in all inertial frames. So what we usually have, that's my picture that in the beginning, a continuous space-time. So this is like warped space-time, let's say, in the presence of gravity. I took some cloth sample from a website, you know, that sells cloth. So this was satin. It's kind of like smooth. That's a continuous space-time. And this discrete space-time would be like this burlap bag that I use for my laptop. This basically, you can only live on these grid points. There's nothing in between. And if that's really true, then Lorentz, special relativity, Lorentz transformations, Lorentz symmetry cannot work in this case. And so a breakdown of any prediction of special relativity, like in this test that we make, would for example, could be a hint of this kind of thing happening, which of course would be huge if we suddenly claimed we suddenly found the smallest thing that can be in the universe. So far we say, oh, there's always something smaller. The more money the government gives us to build bigger accelerators to look something new, the smaller it actually gets. We find smaller and smaller things. Maybe there will be an end to it. Or in a cosmological picture, you could say special relativity means all inertial frames are the same. The physics is the same. It doesn't matter whether you drive by a baseball game. Obviously, the trajectory from you in the car of the baseball is different than if you were at rest in the stadium. But the physics is the same. You just have to transform between the two scenarios. And you will find that the Newton's laws that drive the whole thing are the same. That means all inertial frames, no matter how you move in the universe, the physics is the same. That's what special relativity says. But if it's violated, there could be a preferred frame in the universe. There could be, for example, the frame in which the Big Bang happened, where it blew up from, where the Big Bang was, so to speak, at rest and blew up from. That could be a preferred frame, and that would also be a violation of special relativity. So we can have this kind of cosmological implication of such violations, but also the microscopic one at the length scale, at the Planck scale, which gets me back to sort of my original argument that these things are now really merging. And thank you. And if you have any questions, you could certainly go to this website of mine and find my contact info, my email. So if any of you has questions, I would come by someday and talk about physics. If this hasn't scared you enough yet, you can. It's a very rewarding field, but obviously that's from someone who likes it. Yeah, then anytime contact me. And thanks a lot for your attention. And I'm happy to entertain any questions. That's the problem. We don't teach that in first year because I needed years and years of grasping stuff before you start feeling comfortable dealing with this. Absolutely. Questions? There was someone. Depending on where you're aiming with this question, I mean, this is a very shady analogy. Basically, that the continuous space-time fabric, I shouldn't have used satin, but let's say a plastic foil, that on that foil, your world is sort of on the, and we always have this problem, the real world is three-dimensional plus time, so space-time cannot be really imaged so easily. So this was sort of a simplification that we live on that world sheet, which was that piece of cloth. And if it's continuous, you can move on any arbitrary place on that sheet you can move. Any place is valid. And if it's discrete, then you can't. Like on a chessboard, you can only move from well, you could move your chess piece in any place you want, but your opponent probably wouldn't like it. You can only use from there's really like one spot and then the next one that's discrete. That's sort of like this analogy, but I mean, don't take this cloth thing too far. It's kind of just Yeah, okay, like, I mean, for example, if you look at singularities in that, like black holes and let's say wormholes, where if we take the Star Trek thing further, then we travel through a wormhole. Yeah, I mean, I'm not really in that business, so I'm not really an expert on that. But yeah, there are singularities in the space-time. But let's say an outright rip, possibly. I mean, none of this has been observed. I mean, even black holes have not been really completely undoubtedly observed, even though there's little doubt that they exist. But general relativity theorists, I mean, have all sorts of things that there could be possibly rips and things, but I wouldn't be an expert on that. But yeah, in principle, God knows what happens when you have singularities in there, let's say these black holes that are so massive that they warp space-time to the extreme. In principle, not. I mean, yeah, if, for example, that's a fun scenario. If you observe in our solar neighborhood, like a supernova of a very close by star, the light comes first, And then after a while, the other stuff comes through. So yeah, it might not be here at this moment, but in any case with relativity, since time is not absolute, you have to be very careful what is right now happening in this galaxy. These galaxies are moving relative to us, so you would have to define what you mean by simultaneity is a very difficult, challenging, complex thing in relativity. Things that right here, right in our frame here, let's say we do something at the same time. We raise our hand at the same time, so this is simultaneous. Someone moving by in a fast spaceship sees these two events not happening at the same time, because in relativity, simultaneity is not guaranteed just because you observe it in one frame. So it's kind of like getting a little philosophical. What that means is that star in Andromeda Nebula right now blowing up. And generally, it wouldn't have much consequences. But yeah, I mean, we've seen a supernova in the sky every now and then, and by the time we see the light coming from them, it's been a while, in some sense, that they actually blew up. Yeah, in principle, we don't really know. Since there's no experimental evidence, we don't really know what it would be. But basically what people do is they speculate what could be beyond relativity. They write what's called test theories. They write theories that are different from relativity, but at very slow speeds. They have to converge to special relativity, because in our labs here, we confirm relativity with very, very high precision. So it must be overwhelmingly true. It might only become wrong in very extreme situations that we cannot cover yet with our experiments. And so what that exactly would be, there's many different mathematical opportunities to do things, and which one would work or not. I mean, is it isotropic? That's, for example, what you're asking. Is something in one direction different from another one? For example, is light traveling at different speed in this direction than in this direction? This could all be true. In principle, so there could be anisotropies and so on, but as I say, we would have to find some evidence. So there's a whole community of people working very, very hard on this, basically taking the best technology available to do that.